So as we continue on studying permutations, remember permutations are orders of things that are that where order matters. Basically, we have a group of things, and the order in which they're lined up or they're assembled in a row or whatever, the order really matters. Okay, so if we have 1, 2, 3, a different permutation would be 3, 2, 1, right? So just a different order. That order matters. It counts as a separate and different permutation. Distinguishable objects are objects that are all different. Okay, distinguishable. Just like you or each of you are distinguishable from each other, you're different. There's no one that's completely identical. Okay. All right. So in 4.3, if you want to look at your text, so in your textbook here, what we're going to be doing is solving problems in 4.3, like this one right here. You see this right here? It says how many 3-letter permutations can you make with the letters in the word math, right? And the whole point of this section, there's really 2 main points. You're going to learn how to find permutations of R objects, okay, out of N objects. So if we have 10 things and you want to take 5 at a time, how many ways could you assemble 5 of them out of the 10? Whereas before we were kind of, if we have 10 objects, how many ways could you arrange 10 objects, right? So now we're saying, now we have 10, let's say, people, and I want to pick 3. So how many different ways could I pick 3? Okay, so I could pluck 3 of you out of the group, and then I could arrange you, and then I could pluck another one and substitute and stuff like that. So we'll talk more about that as we move on, but that's one of the things. We have N objects taken, we take R objects at a time, like this question. Okay, we have 4 letters, but I want to know how many 3-letter permutations I can make from that. Okay, so we take 3 letters, we have 1 left over. How many ways can we do that? The other, I guess, main point here is to look at a formula for finding permutations with N objects taken R at a time. There's a bit of a formula there, including, the factorial notation that we studied last section. And also there's a permutation button on your calculator, which you're all going to be very, very pleased with, I'm sure. It's going to make things a little bit easier, okay? So we'll learn how to use that. Okay, so here's the question. That's one of the questions right here, how many 3-letter permutations? So, I mean, I don't know if we'll be able to find all of them, but we can, take a look at how this might look. So let me just clip that and bring it over. So if this was our question right here, okay, so you could start making a list, right? We could go M-A-T. We could go M-T-A. We could go T-A-M. We could go T-M-A. We could go A, and you're getting the picture, right? Right, A-M-T. And then I could switch the letters, so M-A-H, and I could go on. And so it looks like there's going to be quite a few, right? Quite a few permutations if we take 3 at a time. So we're going to find out exactly how many those are, and that involves the formula. Why don't we just go right to the formula? Okay. So when we have N objects, and I want to pick, and permutations, I like to think of, because permutations starts with P, I like to think of the word pick. Okay, so if you get to pick certain letters from the group, and you're going to take R of them. So we're going to fill in these letters, but you'll see this a lot in your textbook, and you should see this on your calculator, NPR. So grab your calculator and see if you can find an NPR function. All right. So let's just, if we examine this, okay, this is the total number of objects that we have. Total number of objects to choose from, or let me say pick. I'm going to say pick because I'm going to use the word choose later, to pick from. And R right here, okay, this is the objects picked, okay, the number of objects picked from the total group, okay, from the group of N. So we have n objects, and we take r of them at a time. And of course, the p means permutation, which means that order matters. Because you see, if order didn't matter, then we wouldn't have all of these as separate permutations. See that? Because these are the same group of objects, but they're just rearranged. So if order didn't matter, and that's what we're going to study when we talk about combinations, just a little heads up. Combinations are when order doesn't matter. And so you would just have, this would be one combination of these three. But permutations means that, hey, the order in which we actually state them matters, okay? So order matters. All right, so let me just show you the formula before we explore the calculator function, because you might not ever go back if I just show you how to do it on the calculator first. But the formula, and if you want to look in your textbook here, page 250 is where they're going to give the formula. So NPR is this. We take the total number of objects, factorial. All right, so this is how many total ways that we could arrange all n objects. And we're going to divide them by the total minus the number of objects that we're actually choosing from. So we're just going to find the difference, and we're going to take that number and we're going to factorial as well, okay? So the difference between the two factorial. So the total factorial divided by the difference between the two factorial. All right, so if we look at this example up here, we have 4 letters, and we're going to take 3 of them at a time. So I have 4 letters in total, so that's going to be my n. And I'm going to take 4 minus, and 3 is the r. I'm going to do that factorial. So, what's, well, let's see, let me just simplify this. That's 4 factorial over 1 factorial. What's 1 factorial? What's 1 factorial? What do you think? Any guesses? Well, it's probably going to be 1, maybe, or what? What else could it be? 1 times, well, we're already at 1. It could be like undefined or something, I guess. It could be 0. Not sure why it would be, but you know, what are your options, right? So maybe you don't know this, but has anyone ever tried to do this on your calculator? What is it? It's 1, okay? So you do this on your calculator, it's 1. The other thing that's kind of tricky, and this is just a bit of an aside, but what is 0 factorial? And does that even make sense? 0 factorial? Do that on your calculator. What do you get? You get 1 as well. Interesting. Okay. Maybe if we have time, we'll explain why this is 1. But yes, this is 1 and this is 1. Okay. So what's 4 factorial? 4 times 3 is 12, times 2 is 24, times 1. So 24. Oops. Does that make sense? Okay. So this is the formula for permutations. Now, if you want to do n objects and you take n at a time, that's no problem either, actually. That's the same as just doing factorial. Because as we just mentioned here, 0 factorial is 1. So when you think about the fundamental counting principle, we have n objects, and we're going to pick n of them, right, all of them, and see how many different ways we can arrange them. And so you could use this formula for that as well. But this formula is also handy if you don't use all of them, okay? All right, so there's going to be 24. So what do we have? 1, 2, 3, 4, 5, 6. Okay, so then we're going to have 6. We're going to have another row of 6. We're going to have another row of 6 and another row of 6. That's actually going to be all of them for this. Now on your calculator with this function, okay, let's test and see how you use your calculator, because we know how to use the formula now. So let's see. Okay, here comes mine. Now, have you all been able to locate your NPR button? With the regular scientific calculator, it should be on just one of the buttons. It should be a second function on just one of your buttons. I think for me here, oh, look at that. That's fun, hey? Calculus. Okay, clear that off. All right. What was I doing? Okay, let's quit that. Let's clear that. All right. So, math, probably probability. Oh, there we go. NPR. So if you're ever using a graphing calculator, go to math, and then over to, oops, sorry, math, and then over back to probability here, and there it is right there. Okay, so how are we going to do this? If we have 4, and then you hit your NPR button, and you're going to choose 3. So you plug in how many total objects you have, your NPR function, and then how many objects you're plucking out of that at a time, and you hit enter. Look at that, 24. Okay? So you do have an NPR button on your calculator, and you really you need to get to know how to use that. Okay? Because yes, you will have to understand and know how to use the formula, but for a lot of the questions, if we have 25 things and you're taking 20 of them at a time, the calculator is kind of a nice way to go, right? Okay, any questions so far? No? Like that 3-second pause there? Okay. All right. Now, let's make some sense of this too. Okay, I want to do this using the fundamental accounting principle. Okay, and maybe I should have done this first, but let's just confirm that this NPR is a nice handy function, and we're going to use this. But you could also just do fundamental accounting principle. Let's say we have the 4 letters, but we're going to in math, but we're going to take 3 of them at a time. So remember how we did this? We did how many choices do we have to make? Well, we have 3 choices for 3 letters. How many choices, or 3 decisions, I guess I'd like to say. How many choices for the first decision? 4, right? How many choices for the second one? Well, there's 3 left. How many choices for the third one? There's 2 left, right? That's 24. So fundamental accounting principle works just as well. And remember what we did? We did 4 factorial divided by 1 factorial. So that's 4 times 3 times 2 times 1 divided by 1. So mathematically, you see how that works out to be the exact same. So fundamental accounting principle works as well. You just still want to make 25 spaces and write things in there all the time. Okay? So that's the basic, that's the easiest type question. I'm going to go over a couple examples where they get a little bit harder and you have to use your brain a little bit more, but that's the base. Everybody got that? Good? Okay. So let's move on to a different example, and I'm going to do example 3 in your text. So if you want to look at example 3, page 250. And let's, example 2, there's example 3, right here. Okay, so let's read through this problem, and let's go through this solution. So, I don't know if that's Tanya or Tania. Anybody know how you'd say that? I don't know, Tanya. I'm going to say Tanya. Tanya needs to create a password for a social networking website she registered with. The password can use any digits from 0 to 9. Okay, so we got 10 options there. And or any letters of the alphabet. The password is case sensitive, so she can use both lower and uppercase letters. So we've got numbers, we've got all the lowercase letters and all the uppercase letters as well. A password must be at least 5 characters to a maximum of 7. Okay? So this is going to be key for this type of problem. This is the type of problem that involves different cases. Okay? So notice the title here. Permutation, problem solving involving cases. So this is key right here. We're going to have to do this problem a little differently than we would some other problems. So you have to, basically we're going to have to test how many different 5-character passwords she could have, how many 6-character passwords, and how many 7-character passwords. Okay, case by case, and then add them all up. All right? Okay, so each character can be used only once in the password. How many different possible passwords are there? Okay. All right, so here's how she did her solution. Okay, and again, when we talk about the number of choices that we have, the n total objects, right? The total number of items. We have 10 numbers right here, and we have uppercase letters and lowercase letters. So that's where you get 10 plus 52. Okay, so that's 62 for n. Everybody get that? All right, 62. Now, here's where the cases come in. Here's our formula. Whatever, you can use your calculator function. But case 1 we need to find out how many passwords are possible when we take 5 of those characters at a time. And so that's going to be pretty easy. We're going to use, I'm just going to skip down here and use our formula. Look at this. So 62 is the total. We're going to pick, and remember, the word pick refers to permutation, which refers to order matters, right? So the order of them matters. 1, 2, 3, 4, 5 is different than 5, 4, 3, 2, 1. So for 62, choose or pick 5. Then we're going to test out case 2, where 62 pick 6, and case 3, 62 pick 7. And then when we get each of those, we add them up. Okay, we don't multiply them. This is not like fundamental counting principle where we multiply these. Cases, you add. You add the totals for each case. Okay, and then there you get your total number right there. Okay, so that's that one. I don't think. Why don't you take a moment here? I want you to do this your turn question. Okay. So just take a moment, take a look at that question, and I'm just going to pause here so you can give this a try. It's very similar to the one we just did. So your turn right here. Okay. So if we have 62 and we pick 8, we get 1.3 times 10 to the 14 different passwords. And which is more secure? Well, is 1.3 times 10 to the 14, is there more possible passwords here or in the original question? Right? Well, the original question was this. Okay? And how many, this is 2 times 10 to the what? 3, 6, 9, 12. So 2 times 10 to the 12-ish. And 1 times 10 to the 14-ish. Okay, so this one's more secure, right? Does that sound right? Okay, so this is more secure. If there's more options for hackers to try and roll through, right? That means it's more secure. Okay. You guys know that. All right, example 4. Let's take a look at example 4. So this is solving permutations with conditions, okay? With conditions. And this one, again, gets a little bit trickier. We're still going to use NPR. You could use fundamental counting principle, too, for examples like this. But let's take a look at what this one says. So example 4. All right. A used car lot, 7 different car models are to be parked close to the street for easy viewing. Okay, 7 different car models. A says the 3 red cars must be parked so that there is a red car at each end, and the 3rd red car is exactly in the middle. So if we have 7, we have a red car on each end and exactly in the middle. And down here, actually, you see they've got the red spots here. Okay, so that's what it's got to look like. Position 1, position 4, position 7 have to be red cars. How many ways can the 7 cars be parked? Well, first of all, I would encourage you to just think about the fundamental counting principle first, because this is not that tough when you talk about the fundamental counting principle. So there's 3 red cars, right? So I have all 3 of them that I could put in the first spot. I have 2 choices for this one, and then 1 choice for the 3rd one. So you can use the fundamental counting principle for these questions with conditions, and sometimes that's easier. So we've got 7 cars in total. How many cars are left? We've got 3 are gone, so we've got 4 left. So any of the 4 remaining could go in this spot. Any of the 3 remaining could go here, 2, 1. So with conditions, sometimes the fundamental counting principle is awesome and is easy. So this one is going to be what? What's going to be the answer here? Looks like 144 if you multiply all that through. Okay? Now how do we do that with permutations? Well, if you think about it this way, the 3 red cars, okay, could be arranged in 3 pick 3 ways, which is basically 3 times 2 times 1, right? 3 factorial. So that's one arrangement there. But you have to consider these other ones as well. And so there's 4, right? Pick 4. for the remaining cars. So if you do it this way, and you think about the fundamental counting principle, you think really what we did is we did 3 pick 3, and then we multiplied, because these are all multiplied, then we multiplied 4 pick 4. So you can do this, times. You just multiply them. And that gets you 144. Okay? So how many different ways could we arrange 3 cars? That's this. How many different ways could we arrange the 4 other cars? That's that, and you multiply those together. So this is not cases, this is all one question, so we can multiply them. Okay? So if you see a question like that, that's what you can do. Any questions about A? All right, let's take a look at B then. B says the 3 red cars must be parked side by side. How many ways can these 7 cars be parked? Okay, so the 3 cars, they have to be side by side. They want them in a group. So if we think about that, 1, 2, 3, there's 3 cars right there. They have to be together, and they could be on the left side. They could be on the right side. They could be in the second position. So here's right after the first one, right? So do you see what's happening? The 3 cars can be arranged in 3 factorial ways, or 3 pick 3 ways. The other 4 can be arranged in 4 pick 4 ways. But now we've got the one group of 3 cars can now shift through the line. Okay? So there's different ways you could kind of look at this one. If you look in the book, the one way that they view this is that they say, okay, well here's the red cars, that's 3 pick 3, right? And because this group can go in any point in the line, you can treat this one as a separate kind of entity and then go like this. And this is what they do. So really you have 3 pick 3 for how many different ways the red cars could be arranged. But then you have 1, 2, 3, 4, 5 different objects that can rotate through, and they can be mixed up. So you have 3 pick 3 times 5 now, if you could consider this as 1, 5 pick 5. And that's 720. So that's one way you can look at it. The other way you can look at it, which might be another good way here, alternate B, is if you continue this pattern that I just started drawing here, and you go 3 pick 3 times 4 pick 4, okay? That's how many different ways these could be arranged times these could be arranged. And then this group could be in 1, 2, 3, 4, 5 spots. So then you could also say, but we also have times 5. And that, I think, should give you the same answer. 3 pick 3 times 4 pick 4 times 5. So that would be 144 times 5 equals 720. Okay? So this is going to take a little bit of practice. I know this all might be new, so it got a little complicated there, but that's kind of what this does, right? You learn something simple, you apply it to a simple situation, and then you kind of get questions that are a little bit more tricky. All right, I'm going to flip now, just going to conclude the lesson here. I'm going to just flip to the key ideas right here. And so there's the formula, okay? And our objects is between 0, so you got to have more than 0 objects at a time, or equal to, I guess, but you can't have more than the original amount that you start with, so that's a little bit of a caveat there. But there's your formula. You know how to use that function on your calculator. All right. So here's permutations when you have 3 letters A, B, C, and you pick 2 of them at a time. So there's all the options that you could have. List out an outcome table. And and yeah, and I'll let you basically look at that for a while. Okay, if you have any questions, anybody have any questions about anything we've talked about so far? All right, I'll put this back up here, but I'll just give you your assignment here as well, and then we'll wrap up. Okay, so 1 to 5, 7, 15, and 16, and 21 is, when I put a box around the questions like that, it just means that it's optional. It's maybe a challenging one, so I would strongly encourage you, if you fly through these first ones, then do 21, okay? Give it a try and see if you can do it, because it's generally a little bit more challenging.